Good evening, this is South Batalha, Astronomy 10, Evergreen Valley College, and this week we are focusing on the evolution of high-mass stars. Um, Part of the discussion that is closing this week, there are several steps in stellar evolution that a low-mass star has to go through. And the point of the one-on-one discussion is to make sure you can outline all the steps. So briefly speaking, and just to review the subject, stars are formed out of a giant molecular clouds, and the main ingredients for star formation is primarily gas, cold gas, can't be hot, cold gas, and then gravity can efficiently start clumping this gas into future stars. And in the process of clamping and contracting and making it denser, it eventually leads to the formation of protostars. So protostars are not stars yet. The definition of a star is something that is visible. You can see like a point source in the sky. I know our book defines star as something that is undergoing fusion reactions in the core. But if that is true, I wonder why we call pre-main sequence stars. So pre-main sequence stars are stars that are not undergoing fusion reactions in their very core, and they are slowly contracting. They are not protostars that happen to be covered by a shell of the gas that is slowly falling and accreting. That's the technical word used, accreting onto this protostar. So pre-main sequence stars is a phase in advance, is a phase where most of this thick gas is dissipated, and now what you're left in the system is primarily a center star still contracting, surrounded by a disk. And out of the material in the disk, then planets, satellites, asteroids, comets, and all of those fun things that exist in our solar system, with exception of the sun, happen to be formed. Okay. So once the star, so in the discussion, you have to go through these steps. So planetesimals are pretty much solid material that is formed in the circumstellar disk itself. And depending on how close this material is formed, how close it is to the central star, you might end up with a solid material that is more rich in silicates or refractory type of materials, or if they are formed further out, they will be pretty much consisting of volatiles types of material. So basically the type of material that is crystallized, that is hardened, or next to the star is, or how far this material is from the star, will determine the type of material that happen to be placed in this location. So you might end up with the refractory type of materials or with the volatile type of materials if it is closer or not to the central star. And then eventually you have your protoplanets and so on, and the planets, and then you start eventually undergo fusion reactions in the core. Now, once the star initiates fusion reactions in the core, we call this star a main sequence, right? It's a main sequence star. And because they stay most of their lifetime, 80% or 9% of their lifetime in the main sequence, then we say, well, most of the stars in our galaxy are main sequence. 90% of them are main sequence, because that is the group of stars that live the longest. So once the star used up all its fuel in the core, so once the hydrogen in the core is all used up, then changes in the center core will occur. And primarily, you go to a next phase where now a core that is primarily helium, you start to slowly contracting and heating up, and then you have the shell fusion around the core. I mean, those are the issues and the points that I would like to see in the discussion. And then because of these shell fusion reactions, and because of now you have a heating core that goes to temperature even higher than it was previously during the main sequence phase, the amount of energy coming out of the central part of the star surpass of what the star had previously in the very core. As a result of this, more energy coming out of the core, the outer layer expands because of the pressure initiated and produced by this excess of energy. Okay. And then as the outer layer expands, then less collision occur in the atmosphere, in the outer layers of the star. Because there is less collision, it's going to be cooler. And for stars, being cooler means redder. So the star expands, becomes red giant. As a red giant, there are changes ensue in the core. Eventually, the core is going to be hot enough for helium to initiate fusion reactions, helium into carbon, the triple alpha process, and then the star becomes somewhat stable in the horizontal branch, fusing helium into carbon and oxygen in the core, up to the point that eventually all helium is used up in the core. And then again, the core starts contracting because there is no more pressure, density, and temperature good enough to fuse carbon into heavier elements. And in fact, the stars, there are high mass stars like those that I would like to show this week. They will have that enough pressure in the core to enable fusion reactions or further fusion reactions of a carbon into heavier elements. And then the outer layers of this star, once the core carbon becomes completely filled, the outer layer expands in what is called the asymptotic giant branch stars. So, and then more processes and more energetics occurs in the core, leading to flashes where the star itself initiates expelling of its circumstellar material, and we call this type of star planetary nebula. Planetary nebula is an expanding gas, has a white dwarf in the very center, and then eventually out of what it was a low mass star, we ended up with a corpse that has a name, white dwarf. So in brief steps, those are the steps of a stellar evolution of a low mass star. And it is true, what controls the evolution of these stars? That was one of the questions in the discussion. What controls the evolution of low mass star is not the size, it's not the temperature, it's not the chemical composition, it's not the location in the HR diagram, sort of. But what controls the stellar evolution is the initial mass of the star. So massive stars, those that have not the big ones, but those that has the most materials, they have enough pressure because gravity is efficient in the core to give enough density, pressure, and temperature that will speed up the rate in which this energy production occurs in the core, and the star goes quickly through its evolutionary phases. Whereas low mass stars, Those with less mass, they don't have that much pressure. And because of that, they take it easy. They take a long time to become main sequence, and they take even longer time to become a giant star, to get off the main sequence. Okay, let me show you a. See if I can find it. If I have it, do I have it? I don't know what it is. Search cost calculus based by the calculator. Oh, there you go. There you go. So if you go to the Astro Interactives, and the link exists in our Canvas course, there are several good exercises if you want to practice this concept of stellar evolution, how exactly that occurs. And stellar evolution boils down to understand what is HR diagram, Hertzsprung-Russell diagram. So in the Hertzsprung-Russell diagram, let's see if I can bring a picture of it. This, by the way, is a core in our course. There you go. This is an example of a Hertzsprung-Russell diagram. It's a diagram that relates in the vertical axis, the y-axis. It relates the energy the star itself produces. It's called luminosity. And in the x-axis, this horizontal axis here, some diagrams present temperature in such a way that the highest temperature is in the left-hand side and the lowest temperature in the right-hand side. So if you look at this HR diagram, in the top left-hand side, you find the most luminous, which means the most energetic, and also the hottest one, because those are, if you take a star at this location, it's going to be a heck of a luminous star, very energetic. But if you drop down to figure its surface temperature, you're going to find a hot member. And I can't even see the number here, can I? Let's see if I can expand that. Oh, this is in colors. Yeah, I prefer to show these in not in colors. I think this is a better one. Oh, that one, temperature. There you go. This better, can see better here. So this, in the y-axis, that is listed luminosity. 1 in this scale represents 1 solar luminosity. So if we take a horizontal line, stars right here, they send out energy that is equivalent to the energy the sun does. So 1 solar luminosity. And in the x-axis, as you can see here, temperature is given in the Kelvin scale. K stands for Kelvin. And it goes from 40,000 Kelvin all the way to about 3,000 Kelvin. Now, the Hertzsprung-Russell diagram, then if you take a star which is located in the upper left-hand side of the diagram, like here, this location represent hot stars because you can drop down. They are relatively hot, but they are also luminous, right? So they are hot and luminous. Whereas if you go down the HR diagram right here, So those are subluminous stars. So they don't put out lots of energy, and they are also cool stars. So how do you build an HR diagram? So you build an HR diagram by observing stars, first of all, and then you determine how much energy the star send out to space. And for that, we use techniques like those we studied previously, photometry and or spectroscopy. And then you determine if the star is luminous or not. You might use certain astronomical candles to determine how far the star is from us, and then we can use inverse square law to figure the amount of energy the star itself sends out. Anyway, astronomers have the means to determine how much energy the star itself is putting out, and also can determine the surface temperature of the stars. So that's how you build an HR diagram. You observe the star, you get information about its exterior temperature, but also the amount of energy they are actually sending out to the space. And then what you found is 90% or more of the stars happen to be situated in what we call main sequence. So main sequence stars are, for instance, our star Sun happens to be a main sequence. Those are the stars that happen to be undergoing fusion reactions. They are actually burning hydrogen into helium in their very core. And this process takes a long time. It's a large percentage of the lifetime of a star. Okay, so that's why most of the stars, if you take a scoop of stars in our vicinity, go up to 20 light years, and then you collect all the stars, you visit all the stars within 20 light years, let's say, and then what you find is that most of them, 90% or more of them, are main sequence, and you're gonna have some that are not main sequence. You're gonna find a few white dwarfs, you're gonna find some giants, and you're gonna find some supergiants. In fact, not a lot of super. In 20 light years, you're not gonna find a lot of them. But if you probe up to 1,000 light years, you might find a large concentration. 90% or more, as I said, of main sequence, and then the remaining are giants, supergiants, and white dwarfs. So this is the HR diagram. So when you observe a star and you are able to probe its luminosity and you probe its surface temperature, so if you happen to place the star in this vicinity here, you can immediately determine the star is a giant, is not a main sequence anymore. Especially if the star is not associated with any site of star formation, in which case you could question your assessment and you could say, well, it might be a pre-main sequence star. But let's not complicate that. So this is very important. So let's go to this exercise. So if you go to NAAP, Astronomy Education at the University of Nebraska-Lincoln, and you go to this exercise, stellar evolution, and then you have a ranking exercise like this. The figures below show main sequence stars of various size. So you have star A, B, C, D, and E. So what you have to do, rank from the least to most the mass of the star. Now, we have to know what a main sequence star is. So when you look at a main sequence star, where is our graphics right here? Okay, when you look at main sequence star, it's not showing in this graph. One of the things we learn about main sequence is that there is a very tight correlation between mass and luminosity, so that the most luminous of them are also the most massive one, and this relation is only true for the main sequence. So those that are the least luminous are the least massive ones. So when you go to this ranking exercise, so its answer becomes simple. This star E is the least luminous, and it happened to be also the coolest one. And star C, it happened to be the most luminous one, and also the most massive one. Okay, so this ranking exercise illustrates a lot what's going on, and then you have more in there. Like exercise number 2. The figure below show HR diagram with points A to F. There you go. A, B, what is C? Oh, right here. C, D, E, F. Various stages in the evolutionary path of the stars. Note that only star B, D, and E are main sequence. B, D, and E are main sequence. So what star A are? So according to our previously displayed in HR diagram, star A are white dwarf, and F could be, I don't know what luminosity scale is, but could be giant or could be super giant. And C is listed as a black dwarf. Black dwarf is a white dwarf like star A that as it evolves, not evolves, but as it cools down, as it loses energy, becomes what's technically called black dwarf. But anyways, rank from the earliest to the latest, the stage in the life of a low mass star without a companion. Omit any stage showing the figure that does not apply. So a low mass star, you would start as perhaps E, right? That's the most recent one. And then it goes to F as a supergiant or no, as a giant, and eventually become a planetary nebula. Since B, D are main sequence, so it's not there, and then appears as a white dwarf, and then eventually as a black dwarf. Okay. And then you try another one. So play around with this interactive exercise, and I think they are very good. Another exercise that I think is very good is the HR diagram that you have in here. There you go. There you go. So again, luminosity and temperature. And then you have stars for comparison like the sun. So if the temperature increases, but the luminosity remains the same. See what I did? I made the star hotter, but with the same luminosity. So this is only true if the star becomes bluer or hotter, right? Right? The temperature is increasing, the size diminishes. Now, if you change the luminosity, then you go to a main sequence. So a star that is a main sequence, right? A star that is a main sequence and has, let's say, 1,000 times the solar luminosity is going to be, in comparison with the sun, is going to be that much big, right? And this is 1 solar radius, 10 solar radius. Now, if the star gets even hotter, right? But if you place it in the main sequence with a radius that's 10 times as big as the sun, right? The star will be, in the main sequence, will be luminous and is going to be relatively hot. So why this HR diagram, this simulation here, help us to understand? So if you compare stars like I'm doing now in the main sequence, those are main sequence stars. So as you probe and go down to stars that happen to be the main sequence, to the right and lower, which means subluminous and relatively cooler, they tend to be small when compared with the sun. In fact, those stars sometimes they even don't have enough mass to even ignite the fusion reactions, the hydrogen fusion reactions in their core, and they are therefore named brown dwarfs. Okay, brown dwarfs. So in this chapter, those are the evolutionary pre-main sequence path of a high mass star. Oh, in fact, yeah, no, I'm sorry. Those are the post-main sequence phase, not the pre-main sequence, the post-main sequence phase of a star that is 8 times or more massive than the Sun. And when the hydrogen in their core is exhausted, then there is no flash. They initiate the fusion of helium into carbon and oxygen right away. And when the core is completely exhausted of helium, is now a carbon core, the carbon initiate fusion reactions immediately into heavier elements, neon, and so on, and so on, and so on. So there is no flash phenomena as it happened, or as we studied in the context of low mass stars, and because the star has enough pressure and enough density in the core to allow for that. And the star, high mass stars go to these different shells where different types of fusion reactions will just be operating in there. And again, here is being indicating the different fusion reactions that are happening not only in the core as the star evolves, but in the shells surrounding the core. So you can suspect the amount of energy that comes out of the central region is such that the star expands to become a large star. Oops. Now, there are pulsating stars, and why these variable stars, Cepheids and R.R. Lyrae, are so important in astronomy. They are important because they have an interesting property, and that is they pulsate in such a way that the time it takes them to complete a period of pulsation, which means when they expand and contract, to initiate expansion again. So the time it takes them to expand and contract, which is called the pulsation period, that time is related to the stellar luminosity. In other words, the amount of energy that comes out of the star itself. Meaning that astronomers can just point the telescope to the stars and then measure the time it takes them to pulsate. And then you have some tight estimate of their energy content, the energy that comes out of them. And by doing so, and using the inverse square law that we discussed previously, you can then determine how far the stars are from us. So if you happen to observe and see these stars in galaxies, you can use the property of pulsating Cepheids to estimate how far these galaxies are from us. In fact, that's how Hubble determined how far Andromeda was from Milky Way. So when this different from low mass stars, as we saw, low mass stars, once they stop all the process of fusion reactions, either in the core or shell, they become a planetary nebula, and they start expelling the gas that surround the core, and the core is then named a white dwarf, and the outer shell are just expanding. Now, with high mass star, something more dramatic happened. The star explodes. The explosion is a catastrophic phenomenon in which the core, which is now an iron core, collapses with a speed that is percentage of the speed of light. Is a very fast collapse, and the outer material surrounding the core prior to the collapse, this material falls like very determined to hit the core. The core is gone, right? So you have gas that is sitting on the core, hot core by the way, and then the core collapses, and now this material suddenly realizes, oops, I gotta go down, and so it drives towards the collapsed core and hits it and rebounds in sort of an elastic collision, and the energy and momentum that is transferred to the incoming gas. So now you have an outward gas that rebounded in this stiff core, colliding with an incoming material, and this crashing, this energy is so magnificent that it's enough to produce what astronomers call nucleosynthesis, and all the heavy elements heavier than iron, are formed in this brief amount of time. I don't know what happened. Oh, that's Renee. Oh, you know what happened? I have a problem with the AT&T. I'm sorry. I have a problem with the AT&T, and my provider, which is AT&T, sometimes shut down. And then without knowing, I got this crazy Xfinity here, which is not my home, and the connection, the speed is just horrendous. And then I lose internet, and I didn't know, so I was pretty much taping, talking to nobody. I didn't know you were not there. Okay, so and then during this brief amount of time, all these heavier elements are formed, nucleosynthesis. But the energy just keep on going, and is so magnificent that you can use that to also see galaxies very far away. And since you have some measured of the amount of energy associated with this explosion, you can, which means you know the luminosity, you can use that together with the inverse square law to estimate the distance to the galaxy itself. Okay. So inverse square law, very robust technique astronomers use. Once you can pin down the luminosity, you observe the object, so you observe the supernovae, whatever they are, and then you can estimate the distance to where the explosion took place. And here's a depiction of this supernovae. And those are the steps in this collapse. Core collapse, temperature rise, and the collapse is such that now these protons and electrons that make up the nucleons, like iron nucleons or any other elements that is still participating in the core, protons and electrons are forced into collision, if I can use that word, and one proton plus one electron becomes a neutron. So the resultant material is a so-called a neutron star, which in terms of a regular high mass star, these nucleons, or this central part, this core is, or this core of neutron, is not big at all. It is 20 miles, 20 miles, right? And the material is so dense that has a density that is similar to the density of atomic nucleus, which is significant. And then the shock waves rip apart the star, go through the star, and then major energy is produced. And here we are, basically, when you look and you see metals around us, and most of the stuff that surround us, with the exception of hydrogen and helium, is pretty much made up in the core of these dead stars that no longer exist. Okay. All right. So again, in these modules that I showed previously, you also can test your knowledge in these different steps of stellar evolution: high mass star and low mass star. Okay. So, and let me know how that goes. If you have any questions, just mail me, and we might be having an exam next week, the third and last one, and I will make sure I announce that to you. Okay. Good night to all of you.